Welcome to GiulioBursiOptics, your channel for non-imaging tutorials. Today we'll talk about the CPC. In the beginning there was light. Yeah, just kidding. We start as we usually do from a circular source, which we represent as a fan of rays leaving it in every direction. The goal today is to make that fan stay inside a given angular range. So, let us draw the range first. A cone opening symmetrically about the axis, at plus or minus 15 degrees for example. The condition we want to satisfy is that no ray leaves this cone. Before designing anything, it is worth asking which rays we need to worry about. If we tilt a single ray and sweep it across the fan, we see that the central rays, the ones whose angle already falls inside the cone, present no problem at all, since their direction is already part of the target distribution and there is nothing to correct. The only rays that require attention are the outer ones, the rays at the extremes of the emission. This is the edge ray principle we discussed in the earlier episodes, applied to a concrete case. If the extreme rays of the source are mapped onto the boundary of the target distribution, everything in between falls inside of it. And the design problem reduces to a problem about two rays rather than about the whole bundle. Among the conics we went through in the previous episode, the one that manages a beam by reflection is the parabola, whose defining property is that every ray leaving its focus is reflected parallel to its axis. If we place the source at the focus of a single parabola and let the ray reflect, the output is certainly inside the angular range, since it comes out collimated along the axis. That, however, is more than we asked for. In a sense, it is the wrong answer. We do not want a very narrow beam sitting in the middle of the cone. We want the light to fill the cone we drew, using the whole angular budget we allowed ourselves. The step that resolved this is to stop collimating along the system axis. If the axis of the parabola is tilted by those 15 degrees, a ray leaving its focus still emerges parallel to that axis, which now means it emerges exactly on the boundary of the target cone rather than in its middle. The extreme ray is placed at the extreme of the target distribution, which is precisely what the edge ray principle asks for. The second ingredient is that our source is not a point but a finite width, so it has two edges rather than one, and each of them needs its own parabola. We therefore build a reflector out of two parabola branches. The right-hand branch is a piece of parabola whose focus sits on the left-hand edge of the source, and the left-hand branch is its mirror image, focused on the right-hand edge. Each branch is tilted so that x-axis makes the target half angle with the system axis, and each one takes care of the edge of the source that lies opposite of it. With the two axes set at an inclination of the target cone, a ray heading toward the right is reflected at an angle that falls inside the fan with respect to the left boundary, and a ray heading toward the left behaves symmetrically. As the reflection point moves towards the apex of the reflector, the reflected ray comes out closer and closer, parallel with the opposite boundary of the cone. Past the apex of the reflector, a ray escapes slightly. We can handle this by either expanding the reflector, or, given that we are working with an extended source rather than a point, by accepting a small penumbra region at the edge of the distribution. If we now displace the source, mirror it, and increase the number of rays, we can see that the whole bundle stays inside the cone we outlined, with the exception of the thin penumbra produced by the outermost rays. which a slight extension of the reflector would move. It is worth being precise about what those escaping rays mean, because it would be easy to conclude that the device is approximate by construction, and it's not. In 2 dimensions, the full untruncated profile is exact for the design condition it was built for. Every ray from the source lives within the acceptance angle. The rays that escape in our simulation escape because we cut the profile short. That cut is a deliberate engineering choice rather than an oversight. The last portion of the profile is long as nearly parallel to the axis, so it adds a great deal of height and material while contributing very little aperture, and in practice a truncated concentrator with a slightly degraded edge is almost always the better choice. This figure, built from 2 parabola branches, is called a CPC, a compound parabolic concentrator, or collimator. The word compound is doing real work in that name. This is not a single curve, but 2 distinct parabolas with different foci and different axes, joined into one profile. I built this figure starting from our own field illumination, so we had a source emitting light and we asked how to constrain its output. Read it in the other direction, the device answers a different question, and historically that is the question it was invented for. Sunlight, for our purpose, arrives essentially collimated, and the problem is to collect it and concentrate it into a small receiver. If we say that we want to accept light arriving within plus or minus 15 degrees, building a reflector of this type with a sensor in the central region maximizes collection, because every ray that arrives within that angular range is delivered to the central zone where the receiver sits. The acceptance angle of the collector and the output angle of the collimator are the same number, seen from 2 ends of the same device. Everything said so far concerns the 2-dimensional profile, where the result is exact. The 3-dimensional device obtained by rotating this profile about the axis is very good but no longer ideal, because rays that do not lie in a meridional plane can, after several reflections, turn back and leave to the entrance aperture. That behavior is governed by a quantity we have not introduced yet, the skew invariant, and it will be a subject of a later episode. Thank you, and see you in the next video.